Anyway, so in this talk, I'll present some Mellanox solutions for in-network computing. We'll talk about how they're applicable to various use cases, and I will showcase some data that demonstrates the performance that we can get with Mellanox solutions. So let's get right to it. So in the context of oh, it is? Oh. So anyways, in the context of network performance for HPC and by extension AI applications, there's some key areas that we can focus on to improve performance. And these are, obviously, first we need to reduce the time that the application is spending in communication. And secondly, we need to do this with minimal host resources. And thirdly, whenever possible, we should aim to overlap computation with communication. Specifically, for AI and ML applications, a key challenge, as we also just heard, is in training these ML systems with frameworks such as the deep learning framework. And in order to improve the training time, what methods exist is to distribute this framework across the system, and in doing so, we introduce synchronization and network overhead. And so as we scale out, the synchronization and the network overhead will increase, and it's just a never-ending cycle. So for data parallel synchronized frameworks, the major computational steps usually are compute a gradient of a loss function using mini-batch, that is to say subset of data on the GPU, and then compute the mean of that gradient across internode GPUs, and using an operation called AllReduce, as we're all familiar with. And then we have to update the model. And we do this until we converge on some solution. So the key takeaway here is also that the latency of exchanging gradients over all GPUs becomes a severe bottleneck. So HPC and Al applications rely heavily on some common data aggregation operations. And here, in no particular order, are AllReduce, reduce, gather, and all-gather. AllReduce for machine learning applications being the most important one, a vector operation that reduces the results and distributes it to all the participating processing elements within the group, in this case an MPI communicator. Reduce, very similar to the AllReduce, except the data is not distributed to all the rings. It's distributed to only, it's sent to only a single processing element, that is to say the root. Gather and all-gather, also aggregation operations, vector concatenation operation. So those unfamiliar with the all-gather operation, the analogy they usually use, if we're all reading a book and everybody's reading just a paragraph, at the end of this operation, we're all going to get all the data we're all going to get. Okay. Same thing. Oh, no, it's fine. Okay.
The voice was in.
Oh. Okay. Oh, so much better. Okay, so these are basic operations, and particularly the one that we're going to talk most about here is the reduction operation. Now, so what are some algorithms that we use today for host-based data aggregation? So broadly speaking, we rely on tree-based algorithms that result in many-to-one and one-to-many traffic patterns. And so these tend to become problematic when we start to scale out, because adding more nodes adds additional tree levels and increases the rating, so potentially causing bottlenecks. So, and then when you go to distribute this data, of course, you run into the same problems which you can rely on. Well, we have some solutions to distribute this data using multicast. So let's take an example with the recursive doubling reduction algorithm. So the data is recursively divided and processed by CPUs, and at each step it has to be processed by the CPU. So when data is exchanged between CPUs, the CPU has to perform the reduction operation, thus rendering the CPU unavailable to perform other tasks. And we've talked about in the previous talk about non-blocking operation, but the problem remains the same. You still have to use the CPU to perform these operations. So the drawback is, if you think about it, that you have to send the data at least 2 times, once to aggregate it and the second time to distribute it. And that also means you have to consume twice the bandwidth. So that's not good. And of course, there exist algorithms that improve upon the host-based design, but by and large, the bottlenecks are still there. So to overcome this problem, Mellanox provides an offload technology called SHARP, Scalable Hierarchical Aggregation and Reduction Protocol. So SHARP transforms the network into a computational resource. So without SHARP, if you think about it, we move the data between compute resources. And with the SHARP-enabled system, the data is processed as it traverses the network. So it effectively turns the network into a powerful coprocessor, reducing the amount of data on the network, reduces the latency, and frees up host CPU memory subsystem for other tasks. So SHARP quite literally fully offloads the operation onto the fabric. So let's take a look at the recursive doubling example with and without SHARP. So in this diagram, okay, we're going to get to that, exciting data. So in this diagram, the blue dots are tasks within a node. So that is to say, we perform first the reduction in shared memory before we proceed to reduce it over the network. The light green dot is the aggregation task. It is a task designated as a node leader which participates in over-the-network data exchange. So when doing a recursive doubling, the data has to be exchanged log n times. So this means that the CPU has to be used at each data exchange step. However, when using SHARP, the data is pushed onto the network, and it's sort of a fire and forget system. Because once you push it, you just wait for the response, and you're going to get the final data. And the data has to, of course, proceed through the SHARP network until a common ancestors for the participating group has been reached, and then it sends the data back. So let's look at some, so we've seen really, really exciting data from the Mvapich group. So here's some data that we've collected on 128 nodes. So in this example, we're showing the MPI AllReduce benchmark difference for 128 nodes between host-based and SHARP-based solutions. So let's see, okay, excellent. So we can observe the effects of scaling for the host-based solution. However, because SHARP offloads the operations onto the network, the latency is only affected by the switch level that you have to absorb, really once, and then the latency remains flat. So in our example, you see for the host-based solution, software 8 bytes, 128 bytes, 128 size. As you start increasing scalability, as you start increasing the scale, so does your latency. However, with SHARP, the latency remains relatively flat. The only observation is that once you increase that tree level, you have to absorb that additional switch latency cost, and then it remains relatively flat. For large messages, because the data has to be processed on every compute node versus SHARP where it's processed in the network, the difference is even more dramatic. So on a cluster of 128 for 1K and 2K, you clearly see the difference in performance between a host-based and a SHARP-based solution. Now, 128 nodes is nice. Here, I present a large-scale example measured at the University of Toronto. You can observe the SHARP-enabled reduction maintains a significantly smaller increase in latency as you scale out. And there's a reason for it, because this is in part that in-node aggregation in our solution first aggregates the data on the host before it proceeds to sending the data onto the network, so effectively transforming SHARP into a 1 ppn problem, that is to say 1 task per node. But nonetheless, the difference is pretty staggering, because at 2K size messages, we're measuring about 12, 13 microseconds at 1,500 nodes. At 1 ppn, that's 1,500 tasks. But then when you increase the scale 40 times, that is to say 40 ppn, you're measuring now 60,000 MPI tasks. And at 2,000 ranks, you can see that for the sizes, you remain relatively fat, and it's really a small increase at that scale versus the software-based solution goes from running at close to 60 microseconds at 1 ppn, and then of course if you add starting more ranks onto the network and more ranks onto the node, you're measuring over 250 microseconds. So a big difference, and I will show some additional data that really demonstrates the ability of Sharp in the context of machine learning applications here shortly. But before that, so let's briefly, and of course now we've heard the Sharp term being thrown around and talked about, but nonetheless, let's very briefly let me mention this. So Sharp is a general purpose primitive designed for HPC and AI applications and applicable to multiple use cases. So it's an in-network tree-based aggregation mechanism that supports large number of groups, and we talked about the number of groups in the previous talk. A group in this context is simply an MPI communicator. So when you create an MPI group, you have to allocate Sharp resources, and if there are no Sharp resources, you have to fall back to the on-host based solution. So let's see. Oh, sorry about that. Where'd it go? Oh, never mind. Okay, so anyways, it's an in-network based aggregation mechanism that supports a large number of groups. It supports some common collective operations: barrier, reduce, AllReduce, and broadcast, and some common reduction operations such as sum, min, max, min-lux, or XOR, etc. Integer and floating point operations up to 64 bits, and up to 1 kilobyte payload size for small messages. That's very interesting, because the quantum switch with HDR capability have a technology called streaming aggregation tree, which allows us to push very large messages onto the network. For accelerating machine learning applications, we also support CUDA, and we have a technology called GPUDirect RDMA, which I will talk about shortly. So I designed this little next set of slides, which should serve just as a little animation on how Sharp aggregation works. So the white stars that you see here are the tasks that participate in a communicator group. The silver stars are the ones that are part of a different group, and then your orange stars are the ones that your switches, your aggregation nodes. So as you send the data out to the switch, the switch will aggregate the data and then send it to the next common ancestor. And this is then done for all the ranks that participate in the network. And so we will fly through this. All right. And once the data has been aggregated, it sends a response back down the tree, and it's sent to all the nodes. So it truly is, you send the data onto the network, it computes it, and then you get it back. So another key technology to accelerate HPC and deep learning frameworks is the GPUDirect, which allows Mellanox network adapters to read the data directly from the GPU device memory. So prior to this, the data has to be staged in host buffers before it can be pushed through the network. So what this essentially means is that the GPU device memory has to be copied to the host buffer. From the host buffer, it has to be copied to the HCA buffer. HCA buffer has to go, send it over the network, send it to the host buffer. From the host buffer, it has to be copied to through the GPU. With this technology, you completely eliminate the CPU bandwidth and latency bottlenecks. You avoid copies through the host, and you use RDMA to transfer between GPUs. And the difference here becomes really staggering. So it's really the fastest possible communication between the GPU and other PCIe devices. So, and it also allows for better asynchronous communication. So, because Sharp supports GPUDirect RDMA, we can directly read GPU device memory and push the data to the remote GPU device. So with these graphs, we demonstrate the performance that Sharp gives when using Sharp in machine learning applications. So we've already discussed what Horvat is a TensorFlow distributed deep learning framework. In this case, we're running the ResNet 15 benchmark, which from my experience seems to be sort of a standard benchmark when measuring. And the performance is measured in how many images per second you can process. So the higher, the better. And there is, of course, an ideal number to this. I don't have it in this slide, but I have how close we can get to ideal with Sharp. In this case, this is we're comparing the NVIDIA and NCCL collective, a very well optimized collective benchmark, against running in pure Sharp. In other words, we're exchanging the data over network between GPU devices. We aggregate on the GPU, and we have to send it back until we come with a solution. With Sharp, on the other hand, we copy the data directly from the GPU and send it to the network, and let Sharp handle the reduction of the data. So, as you can see, we can achieve almost 12% improvement over just pure NCCL, and as we increase the number of GPUs, we improve the performance even more by 16. The major reason for that is because that, if you think about it, in order to do a computation using NCCL, which has to fire up all the GPU kernels, that becomes an overhead. So you would expect when you start processing bigger and bigger data that you're going to see less of a gap, but as I will show you here shortly with Sharp streaming aggregation tree technology, even that gap is really hard to beat. So, very briefly over some of the software that Mellanox offers to use Sharp that we can offer machine learning applications. So I think some of you have heard about this. Mellanox offers these HPCX Toolkit, which is a scalable HPC software toolkit. It's a complete MPI, PGAS, and OpenSHMEM package. The idea is that by using this, you maximize application performance on Mellanox hardware. It's available for commercial and open source applications, and the key is that its intent is to deliver best out-of-box experience. So. It really is just a bundle of binaries. When you download the package from our servers, it's a bundle of binaries for various architectures, Mellanox software versions, and it comes with OpenMPI, our transport, the open source transport library UCX, our collectives library HCall, the Sharp library, and some profiling tools, as well as some standard benchmarks such as OSU and IMB for sanity checking to make sure that the system is running. So where does Sharp fit in the software stack? So on top of the software stack, we have OpenMPI implementation, which has our collectives library, HCall integrated. So if somebody wants to use Sharp, there's really one or two ways to do it. You can either do through a implementation that already has it integrated, or you can integrate it yourself, or you can use HCall, which on top of offering Sharp, it also offers our collective, or our optimized collective library for on-host. So the Sharp architecture, or the components that make it up. The key takeaway here is that in order to run Sharp, you have to have a couple of daemons running, unfortunately, but one being the aggregation manager, which runs on the subnet manager, is responsible for managing Sharp resources such as group allocation, buffer allocation, etc. And then a couple of daemons on your compute nodes. But these daemons are extremely they're very CPU friendly, let's say. So they don't utilize a whole lot of resources, 0%, let's say. They're really, once the application establishes the group, it gets its data, gets its resources allocated, it doesn't communicate with the daemon anymore. So the daemon is mostly in a sleep state. So we're going to go over some data that we've collected. Here's the setup that we use for the data to be presented. 4 nodes, 16 GPUs, TensorFlow, Horvath benchmark running ResNet 50 benchmark, and we will compare this with the standard host-based solutions as well as the Nickel for GPU-based benchmarks running. So the following graph demonstrates the benefit of Sharp compared to host-based reduction. On the left-hand side, the host uses our HCall host-based algorithm, which is still a highly optimized algorithm for host-based data exchange. It's 4 nodes, 1 ppn versus Sharp running up to 256 bytes. So you can already see that in this small for the small message size, Sharp already improves, 50% on the given latency, given which is host-based solutions. Now, the really interesting part is with the Sharp-based streaming aggregation technology for large messages. So OSU benchmarks allows you to run up to 4 megabytes. So in order to demonstrate this, we had to extend the benchmark, and we let it run up to 512 megabytes. So at 512 megabytes with Sharp, you're basically almost 3 times the performance. So that's a significant amount. If you look at the CUDA version of this benchmark, we're showing here performance between the Nickel library versus Sharp when running OSU AllReduce compiled for CUDA. So on the left-hand side, you see pure Nickel library, which I kind of compared the numbers with the previous presenter, and they look about the same, about 30 microseconds here, all the way up to 16K. And but with Sharp, we're measuring about 4 microseconds, so about 10 times it. So this is Sharp with the GPUDirect technology, where we can copy the data directly from the buffer, the GPU buffer, and process it in network. For large data, what I was previously saying, that obviously as you start increasing the amount of data that has to be processed through the GPU, that gap is going to start to narrow. But nonetheless, we're still seeing significant improvements for large messages when using Sharp. The efficiency, therefore, that we can get when we run machine learning is very high. So with Sharp, so again, this is just pure Sharp. This is not using Nickel for on-host based aggregation. We can achieve almost 95% efficiency, which is a very nice achievement. So we have the Nickel benchmark for host-based or for single node aggregation. We have Sharp to push the data through the network. So it's a logical step to combine the two. So here's the here we demonstrate the peak bandwidth as reported by the Nickel benchmark when utilizing Sharp for internode reduction and Nickel for intranode reduction. And Nickel can perform in 2 ways, right? Nickel tree and Nickel ring. And what we've demonstrated when using Sharp combined with on-host Nickel, we can achieve almost twice the bandwidth. And this is almost close to peak bandwidth. This is a typo, I'm sorry. It's supposed to be gigabits per second. So the peak, I think, is at 4 ports. This is for HCX. We can achieve about 80. So with this benchmark, we measure about 70 gigabits per second. So that's so anyways. So I hope that me presenting some data that we can collect with Sharp as opposed to host-based solutions or just pure GPU solutions, you can see the benefits of using Sharp. And yeah, so I'm at the end of my slides, and I will be very happy to take your questions. And if you need, we can certainly talk offline. So thank you very much. Yeah, question.
I have one question. It's around the GPUDirect aspect.
Yeah.
I'm familiar with Linux driver has to, coordinate and call into those. I also know that there is some work going on in the Linux kernel to make peer-to-peer stuff more standardized. And when that gets in, do you plan to migrate your support in Mellanox driver to use that, and/or does the NVIDIA people plan on trying to get their drivers upstream?
Yeah. So I can't talk about our future plans with respect to what you just described. So I don't know if anybody here from Mellanox who's a higher pay grade than me.
So you probably see the patches on the mailing list from Jerome. And he's also provided patches for the Mellanox driver. Borrow driver. Basically GPUDirect income stream. Obviously, we can't talk to what other companies will be doing, but
Even though they'll be using.
I can't comment on what NVIDIA is going to do, but you can assume that a future kernel will have Jerome's patches, the new Varo driver patches, and the Mellanox patches all together.
The PHP-Direct stuff was merged also a couple months ago. PCIe subsystem. There's no support for device attached to memory. Direct transfer bypass in main memory going to device memory, for example.
Can you please come up to that?
Just in time for lunch. Yes.
This will be a short one, so I won't keep you away from lunch. The Sharp that you are using, does that support large messages natively, or are you chunking up messages into 4K, like UDMTU size chunks and doing the communication?
No, we're not doing it. This supports large messages natively, so you can.
Okay, so basically the Sharp V2 with the Spectrum switches. Okay.
Yeah.
Thanks.
Exciting. Okay. Well, anybody else? Excellent. All right. Thank you very much.